So thank you very much. So thank you for the invitation. So the title of my mini course is growth processes. So actually it should have been more precisely said deterministic and random growth processes. I will speak about both things, and actually one of the things I would like to stress is the interplay between deterministic and randomness in this context. So first, I would like to introduce a little bit, make a general overview, and maybe start with an historical overview. So the first growth process that was studied is actually a deterministic one, and it is due to English engineer, actually a naval engineer called Ely Shaw in the late 19th century. So Ely Shaw. So this is something like 1890, and he was studying he was studying fluid dynamics, and he was interested in to see the passage from laminar flow to turbulent flow. Okay, so he invented actually an experience which is very well known from this time now, and it has been reproduced many times, which is called Ely Shaw cells. So how does it consist in? So you take two glass plates which are very near to each other, and between the two glass plates you introduce a very viscous liquid, such as like oil or something like this, very viscous liquid, and through a hole in the one of the glass plate you inject a non-viscous fluid. Okay, so you have here oil. So the fact that you have two plates which are nearby to each other is just to make the process two-dimensional and to avoid gravitational problems which are irrelevant here. So you introduce water with high pressure water inside oil, and so suppose oil maybe is not the right thing. So oil is supposed to be non-colored, and the water is supposed to be colored. Okay, and then we see how the water inside the oil makes a kind of a cluster, and we look at this cluster, which is an increasing cluster, and we look at this how it grows. Okay, so let me show you a picture of this experiment. So this is really an experimental picture. So this is the kind of picture we obtain. So again, the water is in black here. Okay, so the water is colored, the non-viscous fluid is in black, and the viscous fluid is in yellow. Okay, and so we obtain this dendritic kind picture, which is very unstable. I mean, meaning that if you start again the experience, you get something which looks like this, but of course very different. Okay, with the arms are very different, etc. Okay, so this will be a typical shape that we will consider. So this is the first. So this is the first appearance of growth processes, which he showed. And now, one century later, there was a introduction of the so-called DLA. So this is due to two physicists, Witten and Sander, and this is 1981. So this is a very famous paper, very famous. I think it has a record of quotations or something like this. I mean, it was a big revolution when it appeared. And so this is now a growth process. Sorry, it's a growth process, but it's a random growth process. So how did they define this? So they first defined it on a lattice. So you consider the lattice Z square, okay? And so each cluster at time, so the time now will be discrete, okay? So it will be, you will have a cluster Kn, n greater or equal to 0. So Kn is a subset of Z square, a finite subset of Z square. And Kn plus 1 is obtained from Kn by adding to Kn just 1 point, okay? So you start with K0, which is just, well, 1 point, okay? And then what you do is that, suppose that Kn has been constructed. So suppose Kn is such, let's say, something like this. Suppose that this is Kn, okay? Then how do we obtain Kn plus 1? Well, we just start from very far away, okay? Say we start from infinity, and we start a random walk, usual symmetric random walk. That means at each step, you can go either up or down, on right or left. So you have 4 possibilities each time, with probability 1/4 each. Okay, so it's a completely symmetric random walk. So you start this random walk, and eventually, so we know that random walk in Z2 is recurrent. So eventually, you will hit the existing cluster. Okay. So when you do hit the existing cluster, we just keep as a new point the point which is just before you have hit the cluster. Okay. So suppose you hit. So maybe let's take another color. So maybe the random walk comes here and hits here. Then we add this as a new point. Okay, and so and then we have a cluster Kn plus 1. And then we start again. Okay? And of course the idea is to do that millions of times, and we see what we obtain. So of course what we obtain is that we have we fill out the plane in this way. So the way to study this growth process is just to scale the picture so that the picture always stays in your screen. And if you do that, well, you obtain certain shapes, and let me show them. So this is exactly what you obtain after maybe 100 million times. So of course you don't see anymore the little dots, so well, what you see is the center. This was the origin here, and you see such a picture. And of course, the first thing you remark when you see that is that it looks pretty much like the preceding picture. Okay. So they seem to have the same kind of properties. So these kind of dendritic things with arms and etc. And actually, we will show that this is not. We will show the link between the two. We will explain that why they look the same. Okay, this is not a coincidence. I mean, this comes from. Here we have, in the DLA model, we have randomness. In the Healy-Shaw model, we don't have randomness, but we have instability. And in some sense, this instability is kind of randomness. So we will study that more precisely. So now, what is known about these things? So Healy-Shaw flows, we will go. So later on today, I will show you how to derive Healy-Shaw, how to study Healy-Shaw growth, and how to derive it from the equation of fluid dynamics, which is Navier-Stokes equation. So Illy-Shaw flows are rather well known. Okay, DLA is surprisingly completely unknown. So essentially nothing is known about DLA. So we can ask several questions about DLA. So for instance, so if you scale, so you have this cluster Kn, and you can scale it, call it, let's say Kn twiddle. This is a scaled cluster. I will show you later how to exactly scale it. So does this converge in low? Does Kn twiddle? So this is a random set. Okay, this is a random set, so it has a certain low, and does this low converge converge in low? As n goes to infinity. So this is the main question, I would say, and this is we have absolutely no idea. Okay, so this is completely unknown. But we can also ask easier questions. Can I erase here? No, but I mean, can I erase? Everybody has. So now suppose that we do not scale Kn. So we can ask what is the size of Kn. Okay, so we can ask the diameter of Kn. So how does this behave at when n goes to infinity? So it is. Predicted that this diameter has a power law as n goes to infinity. So prediction diameter of Kn scales like n to some power, say, well, let's say 1 over d, because d in this case will be the predicted Hausdorff dimension of the limit. Okay, if we suppose that Kn twiddle converge to something, this something should have a Hausdorff dimension, and this Hausdorff dimension should be something like 1.71 something, and all the simulations show that. I mean, all the known simulations, even with big numbers, and if you do them several times, you always end up with this figure. Okay, so this is a prediction. Nothing is known about that. So first of all, we don't know that there is a scaling limit. This is not known, and of course, we cannot know the dimension of this scaling limit. So the only sorry. We scale the diameter. Okay, so we scale the Kn twiddle has always diameter 1, say. Okay. No, we scale the diameter, and then there is no area at the limit. That's one of the things, which is of course not rigorous, but that's a fact. Okay. The only rigorous result, so known result, which is due to Kesten. So we will not prove this result, but we will prove a similar one for Illy-Shaw flows. So Kesten showed that D is greater than 3/2. Which means that the diameter does not grows like not more than n to the power 2/3. Okay, and this is of course, so if this result is true, this is of course not sharp. But as we will see, so one of the results we will prove is that for Illychow flows, some version of Illychow flows, we will show a similar result as Kesten, that the growth is like a power less than t to the power 2/3 in this case, because now the time is continuous, and in the Illychow case, this will be optimal, because there are cases when you have this. So there is even if we understand the similitude between Illychow flows and DLA, there is still some mystery, because some exponents are not the same for one and the other, and we don't know why. Okay. So one of the purposes of this course is to give. One of the purpose of this course is to give proof of an analogous result for Illychow. And this is actually due to, so this is not due to me, but this is due to Carlson and Makarov. So this will be, so I will speak about that and extend it to another situation that I will now explain. Okay, so that will be one of the goals, to explain that. Okay. Okay, now why did Witten and Sander study this DLA model? They did that because this model was, they thought that it was a good model for actual physical experiments. So let me show you some physical experiments that lead to pictures looking like this. So first, the most important one is electrodeposition. Okay, so you have a solution with ions here, and you put some electrical field there, and what happens is that the ions go so they fix on the pole. Sorry, I don't know the English vocabulary for these things. So the ions migrate here, and they tend to form some solid cluster. Okay. If you have as I do, an old car with an old battery, and if you look at the battery, you see such things, unfortunately, because then the battery doesn't work anymore. So you have these clusters that form on the here, and they pretty much look like the pictures we have seen so far. Okay, but if you do this with different voltages, what happens? Well, it happens this. So this is again pictures with from experiment. So if you increase the voltage, you see that there is, of course, you see that the pictures have the same. They are relatives. Okay, they look the same, but they are not exactly the same. Okay, they look thicker when the voltage is higher, and so the physicists needed a model, needed to introduce a parameter in DLA model in order to explain this kind of differences. Okay, and this is why they introduced a new model called dielectric breakdown model. Okay, so dielectric breakdown model at the origin is just the study of lightnings. Okay, so you have some isolating matter, okay, and you introduce a very high electrical field, and this this isolating matter becomes conducting at some time, and this is through and it appears such things like this, which are exactly lightnings. Actually, lightnings, when you have a thunderstorm, it's exactly this. Okay, so you have the air, which is a little bit isolating, and it suddenly becomes not isolating, and you have these lightnings coming out. Okay, so and we want to study again the shape here. So the shape here it's pretty much like DLA, but very thin. Okay, and if you look at the picture before, you have the same here. You have the same picture, but very thick. So we need a model taking care of those two things. Okay, so now to explain the electric breakdown model, let me come to a off lattice model of DLA.
How do you rigorously define a random walk which starts from infinity?
Yeah, of course. No, I cannot do that. But I can. What I can do is take a big circle, and well, a circle on this square. Okay, so let's say a big square or something like this, and no, maybe you should take a circle. You should take a circle, and points which are nearby the circle, and you choose a point on this circle at random with uniform law.
So it will be a doubling first on the size of the circle, then?
Yeah, but you are right. There is a problem here. No, certainly.
But if you don't need double limit, just take a circle. That's not. You take uniform distribution on a circle.
Yeah, that's what I said. You take uniform distribution and then you start the random walk, and it should be okay. So you take a circle of size, say, 1,000 times the diameter of the cluster, and choose it at random, and then it works. Okay, so before I start with the electric breakdown model, let me introduce off lattice model, and actually this will be the model, DLA model that I will study later. So off lattice. It will still not be. It will be not totally rigorous, but I will make it totally rigorous later in the course. So, okay. So again, DLA deals with a random walk. Okay, so a random walk, you have a heating point on a cluster, so you can ask what is the law of the heating points. Okay, so at stage n, you have in the lattice case you have a boundary which consists in all the points that are just before the boundary, just before the set, okay? And the heating point is one of these points here, and the law that you obtain is exactly what is called harmonic measure, okay? Well, this is the definition of the law that you obtain. So you can now describe an off-lattice model by saying, okay, suppose that you start with K0, which is some compact subset of the, let's say a compact, well, let's say a compact connected. Compact connected. Let's say full, with no holes, okay? Subset of the plane, okay? And now we can speak about the boundary of this as the topological boundary of K0. And you have on this set, you have a harmonic measure. Okay. So we choose a point on the boundary with law equal harmonic measure at infinity. So now this makes perfect sense. Okay. So you can define harmonic measure at infinity of the K0, and then and this is where it is not totally rigorous. We add, a fixed object at this point.
Sorry, what's harmonic measure?
Sorry.
What is harmonic measure?
Well, this is heating probability for Brownian motion, or you can also define it as you look at all the harmonic functions outside K0, so which are harmonic. When I say harmonic outside K0, I mean even harmonic at infinity. Okay, so for this function, which are bounded harmonic function at infinity, you can the value of the function at infinity is given by the integral of the function on the boundary. So u of infinity will be integral over delta K0 of u of z d omega. This is a version of maximum principle. Okay. By maximum principle, the value at infinity is completely given by the values of the function on the boundary. Okay, and it is the integral of this function versus a measure, which is exactly harmonic measure. Okay. Yes.
So are we working on the lattice at the moment?
No, we are not working on a lattice anymore here. It's off lattice. Okay, so I have really a growing family of sets of subsets of the plane. Okay, and then is it okay? Okay, and the illustration of this measure is that it is just heating probability of Brownian motion started at infinity. Okay, and then we add a fixed object, say, for instance, a disk of radius 1 or something like this. I mean, it must be the same object at each step, okay, at this point. Okay, and that's where the thing is not rigorous, because maybe it's not possible. Okay, because if you choose a point which is in some kind of a fjord, maybe you cannot add a disk of radius 1 at this point. Okay, but let's not take care about that now. We will take care about that later. Okay, and this gives this gives K1, and then we start again with K0 replaced by K1, etc. And then we get the off-lattice model of DLA. Okay, so now what is harmonic measure? So let's come back to harmonic measure. Harmonic measure is also, so if K0, so if delta K0 is smooth, then harmonic measure at infinity, this is just gradient of G ds, where G is the Green's function. With pole at infinity. Okay, that is what? That is, what does it mean? It means that G is so G is positive. G is equal to 0 on the boundary, and G of Z looks like log modulus of Z at infinity. So it is, and G is of course harmonic in C bar minus K0. Okay? So this is a definition of Green's function. So it is a function which is harmonic outside, positive, with 0 boundary values, and which grows like log Z at infinity. Okay? And if you look at gradient of GDS, so that's actually the same as dGdN, okay, ds. This is exactly harmonic measure. Okay. So now, what is dielectric breakdown model? Well, we add a parameter in this off lattice DLA. And how do we do that? We do that the most simple way. That is, we multiply. We take an exponent here. We make gradient of g to the power alpha. Okay. So this will be dBm alpha, alpha between 0 and 1. So the process will be exactly the same as DLA. That means that at each step we choose a point on the boundary and we add a fixed object at this point. But now we change the law. Instead of taking harmonic measure as a law, we choose on delta Kn a point with law. So we take gradient of g to the alpha ds. Of course, we have to normalize it so that it becomes a probability measure. So we take this as a law, and we add at this point a fixed object. Okay. So what happens when? So of course, when alpha equal 1, this is DLA. This is off lattice DLA. And what happens when alpha equals 0? So alpha equals 0 is also an interesting process because when alpha equals 0, we just choose a point uniformly on the boundary with uniform law. All the points on the boundary will have the same probability to be hit. Okay. So and this model is also well known and historically is called Eden's model. So Eden was actually a physical doctor who was studying the growth of tumors, and he modeled them as this growth, which is actually growth which is not so, not as interesting as DLA, because it's rather, the geometry is rather boring. Because if you start with a circle, of course, what you will get is essentially circles. Because you always choose at random point with uniform law. So if you start with a circle, you will essentially grow the circle as big circles with noise. Okay, let me show you pictures. So yeah, I will come to that later. I just want to show. Okay, this is Eden's model. Okay, so what you get is growth. Essentially, what you get Kn, it will be a circle with noise. Okay, so this is this new model is supposed to take care of these slight differences that we see in these experiments that I have shown. Okay, now the problem with the electric breakdown model is that it is difficult to simulate. Okay, because simulations of DLA always use the random walk description of it. That means we really simulate a random walk and we look at where it hits the boundary. Of course, we cannot do that here because this measure is not the hitting probability of any random walk, or at least any simple random walk. Okay, so that's why two physicists called Hastings and Levitov proposed a different approach to this, but leading to similar pictures. So this is this will be the main topic of my course. So Hastings-Levitov model. So their idea is very simple. They said, okay, dielectric breakdown model, we always add a fixed object, but we change the law. So let's do the opposite. Let's always choose the same law, which will be harmonic measure. That means that we will always be able to simulate by random walks, but let's add different objects at each step. So so here we choose on Kn we choose a point. Well, on the boundary, we choose a point with harmonic measure at infinity, and we add an object, say a circle or a disk or something like this. They do not precise it. What they add an object of size, say, gradient of g at this point. So we choose a point z. So we take gradient of g here, and we take the power alpha over 2 minus 1. Okay, so that when alpha is equal to 2, we get DLA. And some heuristics in which I do not want to go, say that. So let's call Hastings-Levittov alpha here. So so this will be. I define this as that, and some heuristics say that indicate that indicate that dBm eta will be essentially the same as HL1 plus eta. Okay. So when eta equal okay, so dBm eta was running between 0 and 1, and this corresponds to HL alpha with alpha running from 1 to 2. Okay, so dBm so alpha eta 1 to 2. This corresponds to HL alpha with alpha greater than 1, less than 2. Okay, but now, even if there is no physical significance of the process, at least in this setting, we can. There is no obstruction to taking alpha between 0 and 2. Okay, so actually that's what Hastings and Levittov considered. So Hastings and Levittov considered HL alpha for 0 less than alpha less than 2. Okay, and actually HL0 is an interesting process, and we will speak more about it. We will study it more precisely. And actually HL0 was considered by many people as already been considered by Pomerenke and Rochberg. And it's a funny thing because they called this process SLE. at this time. This was much before, a long time before SLE was discovered, and they called it SLE as for stochastic Loebner evolution, stochastic Loebner equation. Sorry, stochastic Loebner equation. So we will see that for HL0, this is a process which has no physical meaning, but for which we know everything. So for instance, we know that there is a scaling limit, we know the dimension, we know everything. We know how the growth, the speed of the growth, and etc. So we will spend some time on this. And now, what Hastings and Levitov predicted in their paper, so this is a 1998 paper. So they predicted that HL alpha shows a phase transition at alpha equal 1. Okay, and that for alpha less than 1, the growth is rather rapid, with high speed, and for alpha greater than 1, it is rather slow. So it passing from laminar to turbulent growth. Whatever it means, okay, whatever it means. So this was a prediction by and they have done some computer simulations showing this in some sense. Now, I will not, so this prediction is still a prediction, so we don't know, I mean, even how to exactly define it, it's not so clear. Okay, so to make it mathematical, it's not so clear. By the way, I have here pictures of, so this is Hastings-Levitov model for alpha equals 0, alpha equal 1.5. So you see exactly that for alpha small, it's very, the growth is very rapid. And for alpha equals 1.5, it is, it looks more like DLA. I have other pictures which were given by students in École Polytechnique. They have simulated Hastings-Levitov here, and you can see here that for alpha, this is for alpha greater than 1. So you see that for alpha equal 1, the cluster is rather round. For alpha greater than 1 is not round anymore. Here you can see that for alpha less than 1, the growth is rather, so you have rather round pictures. So this shows, in some sense, the so you see here the big difference. Here is for alpha close to 2. It's really like DLA, and here it's for alpha less than 1. So the phase transition is kind of obvious when you see that, but of course it needs to be proven.
Can we consider alpha greater?
Why not? Why not? I haven't done this, so I don't know. I don't know. Or for alpha negative, you can also consider. But
the parameter of phase transition.
So what?
So when we determine phase transition, we usually study some sort of function.
Yes. So this is of course not clear. This was a physicist statement. So they say there is something. So let me now state. I will now state an exact theorem, which will show actually this prediction, but in the deterministic case. Okay, so so to finish with this overview, so now I would like to come back to deterministic models, which are linked to HL alpha. So so again, we have started with Illyshov flows, and we have shown that Illyshov flows look like DLA. Okay, so there is so we have DLA, and there is a deterministic analog of DLA which is Illy-Shaw. So we can look at Illy-Shaw as a deterministic analog of DLA. So now let's define deterministic analog of HL alpha. So this can be done. So using Carlson-Makarov version of Illy-Shaw, so we will define a deterministic analog of HL alpha. Okay, and we will call it HS of alpha, Illy-Shaw of alpha. So, just to give you an idea, so we will of course be very precise in this definition. I don't want to give the definition now because I am just in the overview. So, just to give you an idea, HS of 2 is just Illy-Shaw. HS of 0 will be just the trivial growth by equipotential. What do I mean by growth by equipotential? You start with a shape, okay? So this shape so the complement of this compact set as a Green's function, and you just take the level sets of the Green's function. These make a growing cluster, okay, which is very, very smoothing, okay, because the level sets of Green's function are immediately smooth because Green's function is a harmonic function. Okay, so this is so HS of 0 will be a trivial growth corresponding to HL of 0, which is not so trivial, but can be quite well studied. Okay, and now for this, so we will and we will show the theorem. So maybe that will be the main result of this mini course. And this theorem concerns the speed of the growth of HS alpha. So we have a family KT, t greater or equal to 0 of compact sets growing according to this HS of alpha. So the theorem will say that for alpha less or equal to 1, the diameter of KT will be greater than a constant time t to the power 1 over alpha. Actually, for alpha equals 0, the growth is exponential, which is obvious by what I just said about what it is. So for alpha less than 1, the growth is very rapid. So the diameter grows like at least as t to the power 1 over alpha. So this is due to Stefan Rode and myself. And I will describe that. And for alpha greater or equal to 1, the diameter of KT is less than a constant time t to the power 2 over 1 plus alpha. And this is essentially a version of Carlson-Makarov. So it will be an adaptation, a very easy adaptation of Carlson-Makarov. Okay, and so this shows a phase transition, because if you look at the exponents, then you have 1 over alpha here, and you have 2 to the 2 divided by 1 plus alpha for alpha greater than 1. So at alpha equal 1, you have it's not differentiable. Okay. So the exponent which gives the growth is not differentiable at alpha equal 1, and this is one way of saying that there is a phase transition. Okay. Okay, so that will be essentially the main result I wish to prove.
And I'm sorry, I missed something. Did you say that R of R0 corresponds to the trivial growth?
Yes,
So,
but then the growth is exponential. The size of the at time t is e to the t.
so then the growth.
Yes. So it's very, very fast growing. Okay. Okay, so I think that's about it. If I have time at the end, I will speak about different kind of growth processes. So, for instance, I mentioned in my abstract that I sent growth of cities, because there are models for growth of cities which are quite different from this kind of growth. So I will maybe mention this at the end, but this will not be central in my mini course. Okay, so are there any questions so far? Because I think I have finished my overview now. So essentially, I have told what I would like to say. Yes?
Do you have any assumption to avoid holes to be created in your simulation, or is there no?
Well, actually, no. But actually, simulations show that there are no holes, and I think this is there is a result. Birdsey told me once that he had a student who proved that in DLA there are no holes created, almost surely. I mean, I don't know exactly the precise statement. So what does it exactly mean? I don't know exactly, but maybe with probability 1, after some steps, you don't see any more holes. I don't know exactly. No, this is of course an interesting question. Why are there no? Why all these? This thing could of course make bridges, but they don't. So that's a funny thing. Okay, so maybe for the last 15 minutes, I will now show you Illy-Shaw equation. Oh, okay. So in the last 15 minutes, so there is something that I haven't spoken about. This is a Loevner differential equation. Loevner differential equation will be central in all these things. So maybe in the last 15 minutes, I show you how Illy-Shaw flows connect with Loevner differential equation. Now, for the purpose of the computation I would like to make, I will take a slightly different model, because in the model I have considered here, I inject water into oil, so the part with oil is infinite and contains in point at infinity. Now I would like to make the point at infinity become finite in order for the computations to be easier. Okay, so from now on I will have a cluster of oil, if you want, and the point at infinity will be one point here. And instead of saying that I inject oil, what I say is that I take off oil at this point, and the water will be here. So oil is here, water will be here. So the water will increase and the oil will decrease. Okay, this is just to make the computations easier. So let me just derive the Okay, so we will call v the velocity of the flow. That means that at each point, so this is a field, a vector field. So at each point you have you put the vector, which is the velocity of the flow at this point. Okay. P will be the pressure function. Rho, the density, which will be assumed to be constant. Okay, so we will assume the flow to be uncompressible. And mu will be the viscosity. Okay. So now the Navier-Stokes equation, if you neglect gravity, read like this: dv over dt plus v dot gradient v is equal to 1 over rho minus gradient of p plus mu Laplacian of v, and gradient v equals 0. Okay, so this is a version of Navier-Stokes equation for our situation. Now we will make a series of approximations here, very rough approximations, in order to reduce this horrible difficult equation to a very simple one. Okay. So now we first assume that the flow is steady and 2D. So we assume that dv over dt is equal to 0. First of all, it is a steady flow. Okay, so the speed at each point, and we also assume that it is 2D. So v3, which is v is of course v1, v2, v3, and we assume that v3 is 0, which is not very difficult to admit. Okay, so now this reduces the equation to the following. So we have v1 d over dx1 plus v2 d over dx2. v1 is equal to minus 1 over rho dp over dx1 plus mu over rho, Laplacian of v1. v1 d over dx1 plus v2 d over dx2. v2 is equal to minus 1 over rho dp. And the third equation would be just 0 equals minus 1 over rho dp over dx3. Okay, so we have these three equations. And of course, we have boundary conditions. And of course, the boundary conditions is that the speed on the boundary is 0. Okay, so v1 is equal to v2 is equal to 0 on x3 equals 0 h. Okay, h is just the height, the distance between the two glass plates. Okay, so the first glass plate is supposed to be the plane z equals 0, x3 is equal to 0, and the second is the plane x3 is equal to h. Okay? So now we assume that h is very small and that the flow is very slow. Okay? And this means that we can neglect, well, I should say we may neglect the derivative of Vj, j equals 1 and 2, with respect to x1 or x2, compared with the derivative with respect to x3, towards dvj over dx3. Okay, so in other words, we say that dv1 over dxj is equal to dv2 over dxj is equal to d2v1 over dxj square is equal to d2v2 over dxj square is equal to 0 for j equals 1, 2. Okay. So we completely neglect the variation with respect to the x1 and x2 variable of the speed. And now the system becomes very simple, of course, after having made all these simplifications. And now we get dp over dx1 is equal to mu d2 v1 over dx3 square. dp over dx2 is equal to mu d2 v2 over dx3 square, and 0 is equal to dp over dx3. So this means that p doesn't depend on x3, and if p does not depend on x3, it means that v1 and v2, so this doesn't depend on x3, okay? This doesn't depend on x3, so it means that v1 and v2 are polynomial in x3. So v1, v2 are polynomials in x3, and with the boundary conditions that we have here, we get that v1 is 1 over 2 dp over dx1 times x3 square over mu minus hx3 over mu. We just write that v1 must be, it's a polynomial in x3 of degree 2, which is 0 and 0 and h. Writing that, we easily get this. v2 is equal to 1 over 2 dp over dx2 x3 square over mu minus hx3 over mu. And now what we do is that we take the mean of this speed. That means we write vj twiddle is equal to 1 over h integral from 0 to h of vj. And when we do that, so we compute v1 twiddle and v2 twiddle, and so we get that vj twiddle is equal to 1 over h integral from 0 to h of vj, and so this is minus h square over 12 mu. So I skip the computation, but it's obvious. Okay, and of course, if we put this in a vector, we get that v twiddle is equal to minus h square over 12 mu gradient of p. So we end up with something which is rather intuitive. It just says that the velocity is the gradient of the pressure, which is something which is rather intuitive. Okay, that's the wind. It just says that the wind blows perpendicularly to the level lines of the pressure, which is a rather natural thing. And this is called Darcy's law in physics. Okay, so this is Darcy's law, which originally was created to derive motion in porous media, which is not exactly the situation here, but it's close by. Okay, now let's recall that we have a source or a sink in the picture, okay? And we assume that this sink, actually it's a sink in our situation now, so we have oil, again, I recall that we have oil and we take out some oil from one point, okay? Assume that we do that with a constant speed, okay? With uniformly. If we do that uniformly, then it's easy to see that P well, let's derive this. So we suppose that we take out some oil at a constant rate. Okay. So now the rate of mass change is given by say integral from. Let's take so the sink will be at say x0, and we take a small circle around the sink of radius epsilon, okay? And so the rate of mass change is just rho v twiddles dot n. This is the normal derivative to the circle, and this is supposed to be constant. That's the assumption, okay? Now, using the fact that v twiddle is gradient of p, this is also integral of delta d of x0 epsilon rho, well, say a constant. It's a constant time here dp over dn ds, because v twiddle is essentially the gradient of p. Gradient of p scalar n is just the normal derivative. And then if you use Green-Riemann formula, you get so using Green-Riemann, you get that integral over the disk of radius epsilon centered at x0 of gradient of p dx1 dx2 is equal to a constant. Okay, and that precisely means that gradient of p in the sense of distributions is a Dirac mass, is a constant time Dirac mass at x0. Okay, I do not keep track of the constant here, but I should actually. And what I should do is keep track of the sign, but I will not do that. Okay, so what does it mean here? It means that actually P is essentially times the Green's function. The Green's function of the domain with pole at x0. Okay. So now we get to the point. We get well. I will not be able to derive today to show you how it connects with Loevner equation. So we will do this tomorrow. So, but now it says that the Illychow. So finally, we get that Illychow. So is a motion where the boundary grows is like the gradient of the Green's function. Okay. So the speed is proportional to gradient of g at the boundary. So you have a think of a free boundary, a moving boundary, for which the normal velocity is at every point, at every time, proportional to the gradient of the green function. So this gives the equation of the motion of Illy-Shaw. So tomorrow I will connect this, translate this into the language of complex analysis using conformal mappings, and this will lead to a Loevner equation, and I will speak a little bit about Loevner equation. So let me just finish with one word. Illy-Shaw flow is actually an ill-posed problem. That means that all I have said here, it simply has absolutely no solution in general. If you start with a boundary which is not real analytic, it has no solution at all. So in order to give a meaning to Illy-Shaw flows, and that will be that has been done by Carlson and Makarov, and we will go into that, we need to do something. We need to change the equation a little bit so that it has a solution, and that the solution lives forever. So that's usually in physics they do so-called regularizations or viscosity solutions or something like this. We will do something else connected to complex analysis. So tomorrow I will write down this equation in terms of Loevner differential equations, speak a little bit about Loevner differential equations, and then go directly to Carlson-Makarov theory of Illy-Shaw. Okay.